Hey guys, Zong here, back with another math video. Today we're going to be doing the book stacking problem. The book stacking problem is actually a pretty simple problem to understand, but not a simple problem to solve. So the problem states that you have n books, and you want to, and all these books have the same, so the weight is evenly distributed, and they all have equal weight, and you have n books, and you want to hang n books over a table. So this is the table and the edge, and you want to hang n books over there. And so assuming you have one book, it's sort of like that, it's halfway. And you want to find the maximum distance you can have the books overhang, given an n number of books. So dn. How do you find dn in terms of n? What is the maximum distance you can have these books hang over the edge? That's the question. Pause the video if you need to, or we can go on to the solution. So we're going to use this cool model to help us visualize this problem. It has some of the cases for the smaller cases, and so let's see. So for one book, obviously you're going to hang it over halfway. For two books, this is the ideal configuration. For three books, it's like this, and for four books, it's like this. And the distances, as you can see here, are like this. Seemingly random fractions, but let's see if we can solve this. Now, we need to know first a few physics concepts in order to actually solve this question. And an important physics concept we need to know is the moment of inertia. And the moment of inertia essentially defines it's essentially a property of physics based around a single point. And in order to find the moment of inertia of a certain point, what we do is we need to find the sum of number of forces times the perpendicular distance of that force from the point. So let's see what I mean by that. So let's say we have a point like this, and there's a force right here, and it's going downwards, and we label it F1, and its distance from the point is D. And essentially, it's sort of like there's sort of like a lever arm connecting this force to that point. And let's say there's another force like this that's pushing down with F2 on the end, and this distance is D2. So we want to find the moment of inertia around this point. And in order to do that, we got to add up F1 D1 plus F2 D2. That's the moment of inertia. But wait, actually, it's not the moment of inertia, because what happens is these forces are acting in the opposite of each other. Because when this force pushes on here, the lever arm sort of wants to move this way, but this force is actually moving in the opposite direction, preventing the arm from moving that way, if this is a solid arm and this is a pivot. So actually these forces are moving in opposite directions, because one is moving anti-clockwise and the other is moving clockwise. So in reality, the moment of inertia is going to be F1 D1 minus F2 D2. So that's what the moment of inertia is. And say we had another force like this, F3 D3, so then the moment of inertia would be like this. The center of gravity, the center of mass, sorry, is a point at which the moment of inertia is 0. So moment equals 0. So we have to keep that in mind. Because what happens is in this question, we want to keep the center of the mass directly over the table's edge. Because if the center of mass is over here, that means the entire mass of books on top of the table, the mass is centered at this point, and it's just going to fall over. If the center of mass is over here, it's not ideal, because that means we can shift all the books to the right a little bit and increase the distance. So the center of the mass should be on the edge of the table, right there. So that's the ideal scenario. So in order to do this, let's see how this works. So first we want the center of mass to be right here, but let's see if we can find some other properties or patterns in terms of moment of inertia. And I think an important property or pattern to notice is that all the books on top of the first book, so here, here, and here, their center of mass is actually centered over the edge of the first book. And why is that? That's weird, right? Let's think about this. So let's say we have a table's edge right here, and we have a book right here. And we treat all the books on top of book 1. There are n-1 books on book 1. We're going to treat them all as a single lumpy mass. So this is just n-1 books, right? And let's say, actually I drew that badly. Let's say the center of mass is right here. Is there a way we can make this scenario more ideal and increase the distance d in which the books are stretched? There is. Because what happens is if we sort of shift this book to the left, so let's say we shift the book slightly to the left, the weight on this side is going to be, so let's say the weight on this side of the edge is w. Now the weight is increased by some w plus k, and the weight on this side is decreased. That means that if, let's say n-1 is here, n-1 books, that means we can actually move this to the right. We can move the center of gravity of n-1 books to the right because the weight on this side has increased. So we can actually move this to the right because the moment of inertia on this side has increased. So the moment of inertia, the force has increased, and the distance has increased on this side of the edge of the table, because w plus k is the force, and the distance has increased because we shifted the book to the left. Which means that we can also increase the moment of inertia on the right. So we can shift n-1 books to the right and increase the moment of inertia and balance it out so that the center of gravity is on this. So we can actually shift it this way so that center of gravity is like this. And we can keep shifting incrementally until the center of the gravity is actually on the edge of book 1. If the center of gravity center of mass for the n-1 books goes over, then it'll just fall off. But if the center of mass of n-1 books is exactly on the edge of book 1, then we're fine. If it's not on the edge of book 1, if the center of mass, like in this scenario, of n-1 books is not on the edge of book 1, we can shift book 1 to the left and move n-1 books to the right to increase the distance even more. So good. We have two useful properties. And the useful properties are, if you remember, I got it. Actually, I'm not going to erase it. The useful properties are the center of mass of the entire system must lie on the edge of the table. And the center of mass of n-1 books must lie on the edge of the first book. And do you know what this means? This is an important pattern. This means that when you have case 1, D1, we can place that configuration over the edge of here. When we add another book, let's say this is book 1, we can actually slip another book under book 1 and make book 1's center of mass over book 2's edge and shift the book so that the center of mass is over the edge. And then we can slip another book without moving the configuration of book 1 or 2 so that it's on the center of mass of book 3 and adjust the entire system so that the center of mass is over the edge. And then without moving book 1, 2, or 3, we can slip book 4 into the bottom so that the center of mass of book 1, 2, and 3 just gets the center of mass, what used to be on the edge of the book, just gets shifted over to the edge of book 4. And that's the pattern. So if you look, the configuration of books doesn't move. You just keep slipping one book underneath so that the edge of the book is now is now where the edge of the table used to be. so that the center of mass of n minus 1 books is now over the next book's edge. And that's pretty cool. So as you can see, we literally just took these 3 books and placed them on the 4th book without changing the orientation at all. And I think that's pretty cool. Now here comes the math. Here we go. Let's figure out the moment of inertia around the edge of the rightmost book. How do we figure that out? I wish I could clean this up, but it's all on one layer. So let's see if I can erase this part. Yep, we got. All right. Let's say we have an edge right here, and we have a book. We have one book here, and we're going to treat n minus 1 books as a huge mass again, with the center of mass over here, and this is going to be dn. We want to find the moment of inertia around the edge, right here, this point right here. So how do we do that? Well, first of all, let's say the mass of one book is m. M equals mass of one book, right? So the total mass of the entire system is m times n. The total mass of the entire system is going to be centered over the edge of the table, like we said before. And so the moment of inertia from this point, the distance is going to be d of n. So you want to multiply the weight by the distance, which is the definition of moment of inertia. So times dn. But let's set this equal to something. We can work this recursively. Now let's add together the moment of inertia created from this plus the moment of inertia created from this. So let's think about this. First of all, the moment of inertia created by this is going to be the mass is going to be m, and then the distance. And how do we put the distance in terms? How do we define the distance from right here to there? Well, we know, based on the pattern we figured out before, that when you just slip a book underneath, you keep the entire configuration of the n books beforehand the same. So actually, this is d of n minus 1, because with only n minus 1 books, the edge of the table would actually be right here. This would be the edge of the table. This would be the edge of the table. And that would be dn minus 1. Since we incremented n by 1, we just slipped a book underneath. So this distance right here would actually be d of n minus 1 plus 1/2 of the length of a book, if we assume the length of a book is 1. So the moment of inertia from just this book is going to be m times d of n minus 1 plus 1/2. That's the force. That's the distance. Now what's the moment of inertia of this humongous thing? That's going to be m times n minus 1. That's the force. What's the distance though? Well, the distance is actually just going to be dn minus 1, because the center of mass of these n minus 1 books is right here. So since the center of mass is right there, and the center of mass is dn minus 1 away from this point, that's the distance. So we actually have an equation right here. It's pretty cool. Let's see if we can simplify this. We cancel out the m's. We do some shifting around. And eventually, you're going to get this equation. dn equals dn minus 1 plus 1 over 2n. That's an incredibly simple equation. And let's see if we can put dn just in terms of n. So let's go over here this side. We know that d of 1 equals 1/2, because with one book you just put it over by 1/2 of the length of the book. So d of 2 is going to be 1/2 plus 1 over 2 times 2, 1/4. d of 3 is going to be 1/2 plus 1/4, because this is d of 2, plus 1 over 6. d of 4 is going to be 1/2 plus 1/4 plus 1/6 plus 1/8. So d of n is going to be 1/2 multiplied by 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, which is equal to 1/2 the nth term in the harmonic series. And the harmonic series is just this, summation of 1 over n. So that's actually the answer. D of n is equal to that. So for 100 books, you just do 1 over 1 plus 1 over 2 plus 1 over 3 all the way up to 100. Multiply that by 1/2, and you're going to get the distance that the books can overhang. And I think that's pretty cool. View this cube in this orientation. How many different ways can we view it in this orientation, such that just by rotating this cube and flipping it around? Well, let's set this vertice towards us. This is towards us, coming out of the page, and we set this vertice as 1.